Even if you're not ready yet, just hit record. All right. So how are we doing with the DPQs? So last time we saw, what did you do last time? Exact? I think yes. Exact differential equations. When they're in that exact form, we like them, right? I mean, it's not that bad finding potential functions kind of like you did with conservative vector fields. It's when they're not perfectly exact and we have to find that integrating factor that it can be kind of a pain. But it's still a way that we can get to solutions. So any questions about that we talked about last time? No? All right, you guys are gonna be like this today? Cool. All right, so today we're gonna start looking at applications. We're gonna do applications the next couple of days here, all types of different things. Some that you've seen, or at least I've shown you the differential equations for. We'll go into more depth and detail about them, but let's actually start seeing why we care about this stuff. All right. So the first one I'm going to talk about is going to bring back one that we have discussed before, which is exponential growth and decay. So we'll start easy. In terms of differential equations, these are the easiest, but they kind of build all kinds of other applications from this basic exponential growth. All right, so we have talked about this before, and I have shown you differential equations. Anybody remember what the differential equation looks like that leads to exponential growth and decay?
No.
No?
Y prime is something. Y? KY?
There you go, exactly. So y prime equals ky. And if we just kind of start by looking at this, well, let me also make it an initial value problem. I'm going to make it really, really boring and generic. So y of t naught equals y naught. So that might be times 0, it might not be. It is what it is. Okay, so let's just kind of look at this and see what it's telling us. All right, so first of all, just the equation itself in words, what this tells us is that the population is changing, and I'm going to use the word population whether I'm talking about animals or not. Okay, we can have a population of strontium-90, we can have a population of whatever, right? So it's kind of my go-to is the word, but in this case, the population growth, or no, let me not do that. Let me say it's the change in population, because that's really what y prime is, right? So the change in the population is proportional to the population. So the larger the population, the more we have, the greater the rate of change is going to be. The smaller the population, the less the rate of change. So it's a really basic relationship, but I like to put it in words like this so that you can see how you can apply it to other things. Anytime you find a situation where the rate of change depends only on how many things are there, and so it's just directly proportional, it's going to lead to the same differential equation. All right, so in terms of the solution, we've already seen how to solve this. It is separable. All right, so let me just remind you real fast. You do the y prime over y equal, or sorry, dy over y equals k dt. Gives us the natural log of y equals kt plus c. Right, which then leads to y equals c e to the kt. So there's our exponential bit. And if we've got these initial conditions, then what this turns into, if I plug them in, I get y naught equals c e to the k times t naught. So cy is, or c is equal to this. And if I fire that back in, I get y equals y naught e to the k times t minus t naught. Normally, t naught is 0. We're starting at time 0, which makes that 0. But if we allow it to be anything, this is actually a solution to that initial value problem. So it looks a little bit different, mostly just with that exponent. And it becomes t minus t naught, because when I plug this in for c, I'm dividing by it, and division leads to subtraction of exponents. So that's where that little thing comes from. All right, so we have seen this before, but we really haven't done anything with it. We really haven't used it much. But notice how I say that this is exponential growth and decay. Anybody remember the difference between growth and decay when it comes to this?
K is above or below 0?
Yeah, it's just the sign on k. Whether it's positive or whether it's negative, it tells you whether it's growth or decay. Now, you may just remember that from before, but let's think about this in terms of autonomous differential equations, and then you'll really see it. So this is autonomous, right? He says with confidence. Do you agree with confidence? What does autonomous mean? I think we probably talked about this last week.
Y prime equals everything.
Okay, so it means y prime is equal to a function of y. So it's equal to a function of y, so it's autonomous. Those are the ones whose vector fields had, like once you pick your y, whatever the slope was, it was that same slope all the way across. It was the one that we talked about when we talked about equilibrium values and things like that. So looking at this, what are the equilibrium values for this differential equation? How do we find equilibrium values for autonomous?
When it's equals 0, right?
Yeah, where this function equals 0. Okay, so if we take ky and we set it equals 0, that's only going to happen at y equals 0. So this one's kind of boring in terms of equilibrium and all that. It's got only one equilibrium. And that equilibrium value is y equals 0. So if we've got a population of 0, $0 in our bank account, 0 rabbits out in the field, 0 grams of strontium 90, it's always going to stay 0. Never going to change. Okay, while we're at it, is that stable or unstable?
Looks stable to me.
It looks stable? What does it mean for it to be a stable equilibrium?
Is it pushing away?
So stable is if you get off of it, you're brought back to that value. Unstable, if you get off of it, you go away from that value. And then when it's one direction, you get brought back, the other direction, you go away. Those are called semi-stable. So what do you think? Is this guy y equals 0 stable or unstable or semi? So you're a vote for unstable?
Unstable.
Another vote for unstable?
Unstable, yeah.
Another more head nods? You're gonna hate my answer. It depends. It 100% depends. So just to prove my point, suppose, let's look at y equals, or y prime equals 1/2 y. All right, so let's just look at that example here real quick. So if we do the real quick vector field for it, obviously at 0, our our slopes are going to be 0. When I'm up at 1, my slope is 1/2. When I'm up at 2, my slope is 1. And then it gets steeper and steeper and steeper. And then similarly, if I go to like the negatives, I get -1/2, -1, -2, and so on. Okay, so looking at that one, stable or unstable? 100% unstable. We move off of it, we're going to get pushed away on either side. Okay, but what if instead it's -1/2 y? To draw that vector field, again, it's 0, it's 0. But now when I'm up at 1, I have a slope of -1/2. Then I get a slope of -1, and -3/2. And then on the negative side, they end up being positive slopes. So what's this one?
Stable.
Yeah, that guy's stable. So the problem with just this simple differential equation, if we're going to talk about equilibria, it matters what k is. And this is what leads to either exponential growth or decay, right? So imagine we start off with a non-zero population. If it's a positive k, and we just use the slope field to tell us what goes on, we're going to see something that looks like that as a solution. If it's a negative k, and we start with some initial value, it's going to do that. So there's very different behavior depending upon k. It's either getting pushed away from that equilibrium or being forced to that equilibrium. To me, that's pretty incredible. Like one slight little change, barely change anything. And yet it leads to a completely different solution to these initial value problems. Okay, so this one, like I said, on the left, this is called growth. This is exponential growth. And then the one on the right is exponential decay. All right, so that's how you're going to know which one you're dealing with. And if you're working on a problem that you should have growth, when you go through and you find things, if you get a negative k, you did something wrong, obviously, and vice versa. All right, so for example, let's just say we've got bacteria. Let's slide this over a little bit. So we're going to have bacteria in a petri dish. Suppose that we start with (100 cells, and in 6 hours there are now 1,000. So here's what I want. I want two things. One, let's find an equation for the number of bacteria with respect to time. And then the second thing is I want the differential equation. And we are going to assume that it's just like it's got continuous growth, right? That's not necessarily a good assumption, especially when we start with a small number of bacteria, because it is very discrete, right? It's not like you get partial number of bacterias. Just like now we got another bacteria cell and then another bacteria cell and so on. But for something like that, we can kind of, this isn't a horrible assumption. All right, so we're going to assume exponential growth. So for part 2, we're looking for this. We just have to figure out what k is. For part 1, we're looking for this guy. So we're going to do a couple of things to help us out. First, when it says, suppose we start with, I'm going to let that be t equals 0. I'm going to start the clock for when I've looked at my cells, I've counted them, clock is running. The reason I'm going to do that is if you go back and you look at that formula, the t naught is now going to be 0, which just simplifies the equation a bit. Okay. All right, so yeah, this is what I want. So yay. But now notice we also have some other information. So in 6 hours, that of course means that's going to be a t equals 6. And then the 100 and the 1,000, what do those represent? What letter are those? Those are y's, right? Those are the y values at times 0 and times 6 respectively. All right, well, when it comes to this formula, what's really nice is one of those is c. In this form, when we plug 0 in for t, you get e to the 0, which is 1. So this guy c is just your initial population. So this 100, that's actually c. So we're pretty close. And in fact, answering both of these questions both require the same thing. Finding k. All right. So this is now not a calculus problem at all. Finding k is just going to be an algebra problem. Let's actually use this formula and use that other piece of information. So we know y is equal to 100 e to the kt. But in 6 hours, I've got a number of cells. So if I plug 6 in for t, k is going to equal 1,000. And this is going to be enough information for us to solve. We're going to have to use logs, right, to figure that stuff out of the exponentials, but yeah, whatever. So if you divide by 100, you get 10 equals e to the 6k. Take a natural log to get rid of that e. So the natural log of 10 is equal to 6k. So k then is the natural log of 10 divided by 6. So it's a decimal of some kind. I'm curious, do you know how to tell if a natural log is going to be a positive or a negative number?
If it is bigger than 2.7, right?
Yeah, it depends on which side of e it is. If it's larger than e, which is like 2.71828, it's like pi, right? It goes on forever. So you've got a number bigger than that, it's going to be positive. So 10 is definitely more than 2.7-ish. So this will be a positive number, and we've got growth as we expected. On this guy k, you can really think of this as a growth rate. That's really what k is. It's telling you how quickly the population is growing. Okay, so we got it. We can get a decimal approximation and put it into those, and we've got our answer. So that's kind of your standard exponential growth kind of question. The one thing I'm going to tell you about that you might get, because this is sometimes given to you or is known, is what we call the doubling time. And it's exactly what it sounds like. It's the time it takes for the population to double. And it turns out that it's always the same for any one population. It doesn't matter how many are actually there if it's purely exponential growth. All right, so this is time it takes for the population to grow. And it's actually really easy to find. And go back to the original equation. So remember, we've got our y equals c e to the kt. If our population doubles, we're now at 2c. I can divide by c. Then I can do my natural log. And then divide by k. So here is your doubling time for any exponential growth. It only depends on k. It only depends on the growth rate. The faster it grows, dividing by a bigger number shrinks t, so it takes less time for it to double. So it's not uncommon to see this number, a doubling time. So if they give you a doubling time, you can alternatively use that to find k. K is equal to the natural log of 2 divided by that doubling time. All right, so there's a typical exponential growth. I know you've seen these before, but I'm trying to bring it back to the context of differential equations and how that all works. So, are we okay with that? So while we're at it, let's just real quick look at a decay. So we've got exponential decay, exactly the same, just expect k to be negative. But there's another thing that we often talk about with decay, and that's half-life. So let me really quickly talk about that. So I imagine you've seen that before. A lot of you take in science, and we do a lot of this with like chemistry and all that. What is half-life? Yeah, it's how much time it's going to take for half of your whatever it is to decay. It's kind of like doubling time. You can think of this is the time it takes for the population to get cut in half. So you start with 100 grams of strontium-90. Half-life is how long it takes to get down to 50. And what's really cool is that you can sort of build exactly the same thing for this half-life, doing what we did with doubling time. So imagine we were over here, and instead of going to double our population, we go to half our population. What ends up changing in this equation? Right, it's a natural log of 1/2 instead of a natural log of 2. So you can kind of follow that exact same argument to see that that half-life is the natural log of 1/2 over k. And when it comes to things like carbon dating and all of that, half-life is what we know. I will just tell you from the physics perspective, it's not exactly half of your stuff has changed because radioactive decay is a very random process. It's random. It's like God is playing dice, and every once in a while the dice come up right and decay happens. Okay, so it's very probabilistic. But over the long term, we definitely know how these things work. But other than that, it's kind of exactly the same. It's exactly the same process, right? So, for example, let's say we're doing a carbon-14 dating. So that's probably the most famous one. It works really, really well for things that are only on the order of tens of thousands of years old. If you want to try to date like a rock that's billions of years old, carbon dating will not work for you. That's where you have to use other things. But let's say we're just going to do some carbon-14 dating. And basically how this works, right now, all of us, our bodies are taking in carbon-14. Carbon-14 is created in the atmosphere from solar rays interacting with carbons and whatnot. And we ingest it. I don't necessarily mean eat, but our bodies take it in. But when we die, our bodies no longer are taking in carbon-14. That carbon-14 will slowly decay into other materials. So when they do carbon-14 dating, they basically look and go, okay, what proportion of the carbon-14 is still there? What percent is still there? As if you had been living, and then they can use that to backtrack. Half-life of carbon-14. It's 5,000 something. Let me see what the Google machine has to say. Carbon-14 half-life. 5,730 years. So every 5,730 years, roughly half of the carbon-14 that was present is going to decay. Okay, so here's my question. Suppose we find a bone and we do the dating and we find 15% of the C14 remains. How old is it? So how old is that bone? All right, well, if this is going to follow exponential decay, then we already know what the formula is. Y equals C to the KT. We just need to figure out these different values. So let's actually start with K. How are we going to get K? Yeah, let's use this half-life bit, right? So the K is going to equal the natural log of 1/2 divided by the half-life. So it's going to be the natural log of 1/2 divided by 5730. Let's just leave it like that for right now. Let's not worry about having a decimal value for it. But there's our K. Cool. That's like half the battle, right? There are only two things we don't know, K and C. Well, we just got K. Now, C, we also don't know. We don't know how much carbon-14 was originally in there. But what we do know is that 15% of it remains. It's usually about this point somebody asks me, well, wait a minute, if you don't know how much was there to start with, how do you know that there's 15% left? Because the book said, because the teacher said so. Well, in reality, what they look at is they look at the proportion of carbon-14 to the things that carbon-14 decays into. And you can go, oh, okay, if there's this much carbon-14 and this much of the other stuff, total, 15% of that is still carbon-14. Obviously, you got to be a little bit careful with this, make sure that some of those other things aren't coming from other decay chains, right? But this process is well known. It was invented in the 40s. I don't know what you know about carbon-14 dating at all, but it was one of the guys who worked on the Manhattan Project, building the nuclear bombs, kind of figured this out, that carbon-14 quit being produced when things died, and so figured out that he could use that. And he ended up winning the Nobel Prize in, I think, chemistry for this. Quite a bit after he developed it. Nobel Prize is always a little bit behind, right? Anyway, I'm trying to remember the guy's name. It starts with a W.
Wilbert.
Wilbert? Probably not Wilbert, but it could be. Anyway, all right, so there's our case. So now here's the deal. So we don't know how much we started with, but we know we have 15% left. So think about this formula, the y equals c e to the kt. If I started with c, some unknown amount, and I'm down to 15% of it, how much do I have left? 15% of c, 0.15, right? So we can actually put that into the equation, and we're going to get 0.15 c, 15% of what we started with, is equal to ce to the kt. And it turns out it doesn't matter what c is. Divide out that c. If we're down to 15%, the original amount doesn't matter. So we take our natural log, and I solve it for t. So t is the natural log of 0.15 divided by k. Well, we know k. We just found it. So if we put that in, we end up with a time being 5,730 times the natural log of 0.15 divided by the natural log of 1/2. That's why I didn't bother finding k. I just wait until I'm ready to actually do the computations. So this will tell us how old it is. Now, before we actually get a number, I want you to think about this and make a guess. Because you can make a pretty reasonable guess, I think. Because I think about half-lives. How long until we're down to 50%? It'd be the 5,730 years. So if we only had half remaining, it's about 5,730 years. Okay, so let's say we do another half-life. How much are we down to?
14,600.
Well, let's see. Okay, so one half-life we get cut in half. The next half-life we get cut in half again. So if we were at 100%, we get cut in half is 50%. Get cut in half again? 25%. What if we get cut in half again? 12.5%. So to get down to 12.5% would be 3 half-lives. Well, we have more than that, right? We're still a little bit above 12.5%. So it shouldn't even be 3 full half-lives. Well, 3 full half-lives is like 17,000 years or something like that. So what we should expect when we actually run this number is something not that big, but not far from it. Right? So let's see, moment of truth. So 5,730 times the natural log of 0.15 divided by the natural log of 0.5. All right, and what my magical black box spits out is 15,682.8 whatever. So this bone would be about 15,500 years old. Okay, remember that little mental check? We don't have to go back quite 3 half-lives, when 3 half-lives was 17,000. So we're kind of close to that, but a little bit smaller. That's the other thing I really love about decay problems, is that because we understand the idea of half-lives, it's really easy to cut things in half. And you can use that to give you an idea of how long that or what that value should be. All right, so super easy. differential equation leads to, I mean, honestly, this is pretty easy math. It just involves logs and exponents, which is why we don't like it. But in terms of complicated stuff, it's not that bad. All right, so let's bump it up a notch. Let's look at some other things that are like exponential growth and decay. All right, so here's the next example I want to show you. I want to talk about compound interest. All right, so has anybody heard of compound interest before? You've heard of it? May not know what it means or what it does. Anyone know what it does?
Normally not good things.
I'm sorry, say it.
Normally not good things.
Normally not good things. It depends which side of the equation you're on. All right, so you know about interest when it comes to loans, right? So interest is a payment that you make to borrow money. Right? But you can also get interest paid to you, like if you've got savings account type things, right? Mutual funds, they'll talk about kind of interest rates you get on that. So interest is basically money earned or paid when monies are loaned. And there are two kinds. There's simple interest and there's compound interest. Simple interest is like kid interest. It's I'll loan you $1, and then every day it takes you to pay me back, you owe me another nickel. Right? So if it takes you 5 days to pay me back, you owe me $1.25. It takes you 10 days, then it's $1.50, so on. Right? Kid lunch money kind of interest. I'm sure we've all been on one side of that equation when we were kids. All right, so that's simple interest. But the world doesn't work on simple interest, it works on compound interest. And compound interest, the way that works is any interest that's accrued gets more interest on top of it. So remember when I said, have you heard about this? What do you know about it? Jackson's like, well, it does bad things. That's the bad side of it. Like, credit card debt is a great example, right? So suppose you have a credit card and you go out and you charge $5,000 and you don't pay it back. Okay, well, they're going to charge you interest on top of that. So now all of a sudden you don't owe just the $5,000, but the $5,000 and their interest. Well, if you don't pay it back then, not only does your original $5,000 earn interest, but the interest that was already charged to you gets charged more interest. And the next thing you know, that just grows out of control. So that's the bad side of it. The good side of it is, I just deposited $1 million into a savings account. I didn't, by the way. But if I could, right, I put it in a savings account, I earn interest. Well, that interest gets paid back into my account and then subsequently earns more interest. You know that saying, it takes money to make money? That's one of the examples, right? If you can just put money away, it will earn money on top of itself and grow very quickly. I'm sure you probably have heard this, that if you're going to start saving money, start doing it when you're young. I know that's easy to say and not so easy to do when you're a poor college student. Trust me, I didn't either. But if you can, then there's more time for it to build upon itself. Well, that's compound interest. Now, compound interest, I'm not going to show you a differential equation for it just yet. I'm just going to show you what the formula looks like. And then we'll talk about how this has anything to do with differential equations in a minute. All right, so here's the formula. How to read all this stuff, what all this stuff means. So P, this is the initial amount. In the context of economics, business, P stands for principal. So it's the principal of your loan. So you go buy a house, take out a mortgage. you're like, okay, I'm going to get $400,000 mortgage. That's your principal, $400,000. R is your interest rate. So your 5%, your 7%. In case of credit cards, your 20 whatever percent. Credit cards are horrible. If you get behind on credit cards, it's really bad because interest rates are so high. All right, so that's your interest rate. T, of course, is time. And then there's this N. And what N is, this is the number of compoundings per time period. So compound interest, there are lots of different forms to it. And a lot of it just is how often they calculate interest. So for example, usually T is in years. So N will be the number of times per year that they compound it. So for example, a savings account. Like you go down to Bank of America, US Bank or something like that, you get a savings account. They often calculate your interest monthly. And if that's the case, then N is 12. Because they're going to calculate it 12 times a year. If they only do it every 3 months, N is 4. Right? Something like that. Credit cards. Do you know how often they calculate your interest? You got to read the fine print on this. If you look at the back of your statement, it'll tell you.
Is it by weekly?
It's worse. It's daily. It's based on your average daily balance. So they do a daily calculation. So if we're going to do a daily, what's N? It'd be 365. Okay, so here's the deal. The bigger N is, the more the account balance will be. Just plain and simple. So if you only calculate once a year, N equals 1, you're going to end up with a smaller amount than if you do it every month, which is going to be smaller than if you do it every day, so on. But what's interesting, and this has been known for a long time, by the way, interest rates and compound interest, there's evidence of this from stone tablets in Babylon. So like 4,000 years ago, they understood compound interest. And what even they knew at that time is that as you increase N, you get more, but it flattens out. Like the difference between monthly and daily isn't as big as you might think. Or if you went, okay, well, instead of daily, what if we do it every second? Even if you increase N that much, it doesn't change a heck of a lot. It kind of levels out. All right, but here's what I want to do. Let's look and see what happens if we take a limit as we go to infinity on this thing. And I don't mean as t goes to infinity, because I already know if t goes to infinity, this is going to blow up because it's exponential. But what happens to this formula if we let n go to infinity? So that just means compound more and more and more and more and more. So instead of every day, every minute. Instead of every minute, every second. Instead of every second, 1,000 times a second. Now, it gets to the point where procedurally this is difficult. Maybe not so much with high-speed computers now, but you can imagine you're a Babylonian doing all this stuff in clay and sand, trying to calculate interest more than every day. It's probably difficult. But we've got computing power that lets us. So what if we instead just say, well, let's let n go to infinity. Let's see what happens. Okay, well, the p is a constant multiple, right? That's just how much we put in initially. So let me just pull that out. But let's look at the limit of this other bit as n goes to infinity. And in fact, I'm going to write it like this. Since the t doesn't matter in terms of the limit, let me just kind of pull out only the stuff that matters. So imagine just plugging in infinity, because that's always our first go-to when you do a limit, right? Just plug in the number. R is a fixed decimal. If I divide that by a super big number, that's going to eventually drop to 0. So what I've got in my parentheses is 1. And then I'm taking 1 and I'm raising it to the infinity. So if I just plugged it in, I'm basically getting 1 to the 0. Anybody know what that limit is?
1.
1? E? You both might be right. This is an indeterminate form. Kind of like 0 over 0, or infinity over infinity. 1 raised to the 0 is indeterminate. It literally could be any number. All right, so how do you figure out those limits? Do you remember what you did to find like a limit that when you plugged in was 0 over 0? Use L'Hopital's rule. So we're gonna have to use L'Hopital's rule on this thing, but this is not the right form for L'Hopital. L'Hopital can only work 2 forms, either 0 over 0 or infinity over infinity. So this is one of those where we have to pull a little trick. I'm gonna let y equal 1 plus r over n to the n. And then I'm gonna take a natural log. If I take a natural log, I can bring that exponent out front. And now I've got infinity times 0. And infinity times 0 is still indeterminate form, but it's really easy to make that 0 over 0. I can just write it like this. And now I've got 0 over 0, which is going to let me do L'Hopital's rule. All right, I don't know if you remember this trick from back when you saw L'Hopital's rule. It was forever ago. First quarter calculus, I think is where you first see that. Is it first quarter? I don't know. And wherever you saw it in the first year, L'Hopital's rule. All right, we get here now, we can do it. Well, if I do L'Hopital's rule, I'm going to spare you a little bit, just a little bit. In terms of what this looks like, on top, since it's a log, the derivative of that is what's in log on the bottom, and the derivative of what's inside on the top. So it looks like that. And then 1 over n, its derivative is minus 1 over n squared. You can just trust me on this, or come talk to me either way. But now when you simplify this, like these n squareds cancel, that minus sign cancels, and you're left with just r over 1 plus r over n. So we're looking at the limit as n goes to infinity of r over 1 plus r over n. And that one we can calculate. What happens when n gets really big? The piece with n gets really small, so the bottom turns into 1, and r divided by 1 is just r. Okay, now, that's not what y is. That's what the natural log of y is. So what does y equal? E to the r. Yeah, so if natural log of y goes to r, then y goes to e to the r. Okay, so let's look back at this guy. So now we have p times e to the r raised to the t. And that gives us the formula a equals p e to the rt. All right, so you recognize that. If you don't, let me just draw your attention over to this board. Letters are changed, form is still the same. So it turns out that compound interest is actually exponential growth. If you are always calculating interest, like always, nonstop, that theoretical world, it turns into just exponential growth. So that's another place where we can actually create differential equations to model what's going on if we want to talk about money and interest. So savings accounts, loans, and that sort of thing. Because what would the differential equation look like for this? If our quantity is A, we're now going to have A prime. If it's exponential growth, it would be K times A, but what's K in this case? It's the R. So all we need to do to build our differential equation if we're involving money is your interest rate. So let me show you an example. Suppose we win the lottery. Yes, we just won the lottery. And what we're going to do is we're going to put $2 million of it just into a savings account. Like, we're not going to touch it. Okay, so if we did that, then we would, whatever the interest rate is, we could follow this, and we'd see our money grow exponentially. But because we're humans, we're not going to just not touch that money. We're still going to enjoy it. We're going to have some fun. All right, so for example, let's say we're going to deposit $2 million, and we'll put it into an account that's earning, just to make numbers nice, let's make it 5%. And we'll go ahead and compound it continuously. So we don't have to worry about N and all that sort of thing. We just get to go to PERT. Okay. But because we, are kind of excited about having this much money, suppose that we take out $250,000 a year. So that's going to be our living expenses and everything. And I see all your faces. Can you imagine having $250,000 a year just like live off of? Oh, beautiful. All right, so here's what we're going to do. We're going to do two things. One, let's build a differential equation for this situation. And then two, let's solve that differential equation so we can get an equation telling us how much money is in our account. And then step number 3 is going to be, when do we run out of money? And I'm just going to tell you, we are going to run out of money because we're taking it out faster than it's getting put in by interest. What's 5% of 2 million?
100,000. Oh wait.
So 10% would be 200,000. So 5% is 100,000. Okay, so we're only getting $100,000 put into our account from interest just as it is, and we're taking out more than that. Okay, you know what? Let's do this. Let's be not quite as extravagant. You think you could live off $150,000 a year? I'm pretty sure I could, because that's more than I earn right now. Okay, so let's be less extravagant. But still, we're taking money out faster than it's getting put in by interest. All right, well, let's start with the differential equation. So, my A prime, it's going to equal R times A. So we're going to get our 0.5, whoa, not 50. I wish I earned 50%. If I could find any account that gave you 50% interest, I would literally sell everything I had and put every penny in that. All right, so here is our gaining from interest. But that's not all that's going to be in our differential equation. What else needs to be in there? How else is our account balance changing?
The money we take out.
It's also, we're losing the money that we take out. So I'm going to have to subtract. And what I'm going to subtract is that $1,500 per year. I really just think this A prime, how is our balance changing? Money's coming in and money's going out. All right, so there's the differential equation that models this scenario.
For a year.
What's that?
For a year.
Yeah, so this is where our time is in years. Classify that for me. What type of differential equation? Ooh, is it exponential decay?
Is it?
That's actually not what I was going with classifying it. I meant like go back to the very beginning of class. Like what type of differential equation is that? What order is it?
First.
It's first order. Is it linear?
Yes.
Yeah. Is it separable?
Yes.
Yeah. It's also autonomous. So it goes by lots of different names, but it's linear first order or separable, which regardless means we can solve it. Now, is it decay or not? Not really. Let's wait until we see what the equation looks like once we're all done. And then we'll talk about decay versus not. Okay, but this is linear first order. Cool, piece of cake. We know how to solve those. So let's do it. Let's solve this guy. So I'm going to put it in the form that we like. Move that A over here. So for linear first order, we got to find our mu. And mu is going to be e to the integral of the p. So that's that guy right here, which is going to be e to the minus 0.05 t. Okay, so there's mu. So then our solution is going to be A equals 1 over mu times the integral of mu times g. All right, so let's do that real fast. I'm going to write this as a positive e to the 0.05 t, so fraction 1 over. And then the integral on this guy, when I integrate the e to the minus 0.005 t, I get that same thing, but divided by 0.005. So we're going to get whatever 150,000 is divided by 0.05. Get that real quick. My brain is definitely too tired to do this math. 3 million. So this ends up being 3 million e to the minus 0.05 t plus c. All right, so let's distribute that through, and then we'll find our C value since we have an initial condition. So let's see, that's going to give us A equals, A equals 3 million, because these e's are going to cancel, plus c e to the 0.05t. Now let's use our initial condition. At time 0, we have $2 million. So 2 million equals 3 million plus c e to the 0. Well, e to the 0 is 1. So that tells us that c is minus 1 million. All right, so here you go. So there's the formula for our account balance. Notice that when we plug in 0, it does start at 2 million. But now we can find out how much we're going to have at any point in time. So for example, what do we have in 10 years? Well, it's going to be that 3 million minus 1 million times e to the 0.5. Let's see what that gives us. Any guesses on approximately how much that is? Sorry, I'm just curious.
1.6 mil.
We're still doing pretty well. After 10 years, we're at 1.35 million, so pretty close.
I was gonna say that exact number too.
Oh, were you?
Yeah, just didn't give me a chance.
Oh, sorry. I should have given you another minute.
Yeah.
Apologize. That was rude of me, Jackson.
Yeah, that's alright.
Okay, so, I mean, we're doing pretty well, right? In 10 years, we still have 1.3 million. Okay, what about in 20 years? Okay, the only thing that's going to change is instead of that 0.5, 20 times 0.05 is 1. So if we change that in 20 years, like I'm blaming the calculator, not me. This one, apologize for this. Either one.
200,000.
Okay. In 20 years, we're down to very close, 281,000.
Isn't that just
No,
No. Oh, that's
no,
I was
but
thinking.
it's not far from it. Okay, but notice that huge drop. In 10 years, we spent $650,000, or our balance dropped $650,000. In that subsequent 10 years, it dropped almost or over $1 million. Okay, but still, I mean, think about this. You've now had 20 years of pulling out 150 grand every year, and you still have that much left in there? That's not bad. Okay, so here's my question. When do we run out? When do we run out of money? How long can we play this game? Pulling out 150 grand a year. All right, well, the answer to that is going to be just set A equal to 0, right? So if we do that, then once I kind of move things around, I'm going to get e to the 0.05t is equal to 3. If I divide by 1,000,000, I'm going to get 3 minus that e equals 0. So then I just take a natural log, and then divide by that 0.05. All right, Mr. Smarty Pants.
Oh, like.
So I just put the pressure on. I
uh,
don't work well under pressure. Well, let's just think about this. It's not going to be very long, right? Like if we accrue no more money, how many yearly payments can we pull out?
2.
Around 2, right? So we're only at about 2 years left with what's in there. Now we are going to be gaining some more, right? So getting another 2-ish years sounds pretty reasonable. And in fact, that's what this is. It's around 21.97. All right, but check this out. This was 100% using differential equations to model our finances. I'd probably be all right. 22 years, that puts me at 73. I can fake it by the time I get there, and plus the world's gonna be over by then anyway. But really, what we would want to do, like honestly, what would be the best case scenario here in terms of what we're gonna pull out?
Maybe just pull out 100K.
Right? Like if we pull out 100,000, what's gonna happen to our account?
Last longer.
Not only will it last longer, I think it'll last forever. Right? Because how much are we getting in interest? 100,000. And in fact, if you were to change this to 100,000, what's the equilibrium for this? It's autonomous, right? It's got an equilibrium value. You set this equal to 0 and solve, and it'll be A equals 2 million. So if we wanted to make this last as long as possible, we just make sure that we only pull out $100,000 a year. We take out our interest. Now probably what we'd want to do is take a little bit under so that that could still grow. But there are a lot of accounts that do this. I know a lot of you are applying for scholarships, probably have gotten scholarships. Have you ever heard of an endowed scholarship? So an endowed scholarship is one that just like lives on in perpetuity. That they're like, no, we've got enough money that we can always give out $1,000 a year. And the way they endow it is by getting a certain amount that's in the account so that it earns as much interest as that scholarship, right? So if I've got an account that's earning $1,200 a year, I can give out $1,000 a year without having to worry about it. And in the next year, I'm gonna re-earn that 1,000 that I gave away, and so on and so forth. So this is a thing that is done quite a bit. Now I know for us this is sort of a fanciful, hey, I just got $2 million to put it away. But I promise you, like if I won the lottery, I'd have to play the lottery first, and it's a sucker's bet, so I don't, right? Although there are times when the expected value gets high enough that it's worth it. Like with some of those like mega bucks and all that. It's still a sucker's bet. But if I were to win, I 100% would do this. Like let's.
There's a positive EV you gotta buy.
I mean, that's what they say. I don't got to. I don't. Because the problem is that that's anticipating an infinite number of trials. And you can't have it like, you can't buy it in. Actually, what you should do is if there's a positive value, go ahead and say, I want every single number combination. They don't let you do that. You got to actually print them all out and everything. And then that can't happen. There's not enough time for those machines to do that. But anyway, my point is I would take a big chunk of it, just put it away and be like, no, this is what I'm living off of. I'd probably allow for a little mad money craziness at the start.
Yeah.
You know what I'm talking about. Like, oh, you went to every single Mariner game this season? Yes. Yes, I did. Even the ones that were in Toronto and yes. Yes, I did. But you know, if you just put it away, no, you'll be set. I'm telling you, like sports stars, give me one salary. I'll take like Mike Trout. I will take 1 year of his salary, and I will be good forever. That's all I need.
What's the salary?
Oh, it's in the double digits of millions a year.
Jesus.
Yeah, like those guys win the lottery every year. Now, I'm not saying that they didn't have to work hard to get there, and those of you that play sports know it's not easy to reach that upper level, so I don't fault them for it. But I'm like, man, I only need one. You know, I don't need a 10-year contract. Give me a 1 year contract. I'll do pretty much anything you need for $15 million for 1 year. Anything on that baseball field you need, I got it. 100%. Anyway. All right, so here's another one that, now, is this exponential growth? Is it exponential decay? Let's come back to that, right? Because when I first put this up and I was like, what kind of equation? Right? I had said, oh, it's decay. Is it exponential decay? Like, there's no doubt our balance is decreasing.
That's still
Right?
exponential growth.
We see that. But is it exponential decay?
So,
Right? And it's not, because there's no negative up in here. Well, we've got exponential growth that's being taken away. And that's why we actually start running out of money. Is that this bit that's getting lost is growing bigger and bigger and bigger with time. Exponential decay has an equilibrium. And what kind of equilibrium? Was it stable or unstable?
stable.
For decay, it was stable. It was going to 0. This also has an equilibrium. Like if I change it now, it's at the 2 million. Is that stable or unstable? If I step off of 2 million, do I get brought back to 2 million?
No.
No. So what ended up happening here is this is still an unstable equilibrium because of the positive K. This just happens to be one that we are now allowed to be on the underside of the equilibrium, which regular exponential growth we don't see. I don't have the picture anymore, but regular exponential growth, 0 is our equilibrium. So we're always like above it and just growing. Right? This one, we're allowed to be below, and so now we can drop down from our equilibrium. Anyway, so another example that's not exponential growth, but like a little bit more. Okay, let me show you another example that has nothing to do with money. This has everything to do with populations, and I kind of already hinted at it when we were doing those autonomous differential equations the other day. Let's look at carrying capacities and thresholds. So this exponential growth doesn't really work as a model as time goes on, at least for very few things, because as time goes on, it will grow to infinity, or in the case of the one we were just looking at, it'll drop to minus infinity, and there's no such thing as a minus infinity bank account, and there's no such thing as an infinite number of bacteria, and so on. So once we start introducing carrying capacities, it definitely changes the differential equation. So let's look at population modeling here. So you've got regular old basic exponential growth. and that's our P equals, or P prime equals KP. Right, so we've already talked about that. But that's not so great in terms of actual modeling. So let's throw on a carrying capacity. So you remember what that was? Talked about it last week.
Maximum amount you can have.
Yeah, so it's the maximum number the population can be due to resources and space and whatever, right? So carrying capacity, this is just a maximum allowed P, where if you're bigger than that, you will drop back down. If you're less than that, you can still grow to it. And we had a differential equation for this last time. And it kind of started the same way. I'm going to use L to represent our carrying capacity. And what we had to throw in there was an L minus P. So I showed this to you last time, but we didn't talk about it though. I just kind of said, here's the differential equation. This is what it's going to do. We looked at its slope field and all that, but let's kind of talk a little bit more about it in depth. So it starts kind of the same way, KP. So it's saying we would have exponential growth as long as we're far away from L. If we're far from L, this thing, if population is far away, then, you know, whatever, this is irrelevant, and it's grow kind of exponentially. But as we start getting closer to L, this number starts getting really small. So we have a small multiplier, which is going to decrease our slope. So it's going to cause our population to start leveling off. In terms of equilibrium values, there were two. What are the equilibrium values here? What P values make this 0? 0 and L, right? So we can have two equilibria. So P equals 0. The infamous, you got to have some to get some, whatever I said the other day, right? So if we're at a population of 0, nothing will change. And also P equals L. So if we're at that carrying capacity, we stay at that carrying capacity. But they're drastically different in terms of what they do. 0, stable or unstable? Stable? Unstable? How do we tell? Let's review that. How do you tell, given an autonomous, whether or not it's stable or not?
Plug in numbers.
Okay, so we're going to plug in numbers. We could actually draw the vector field, the slope field, and look at it, but it's a little bit faster. I showed you that picture I drew that looks like this, where I put my equilibrium values. And then I just look at what is my derivative on either side of this. So like 0, for example, if I plugged in a negative for my P, this would be negative, this one would be positive. Negative times positive is negative. So my slope is negative, which means I'm decreasing. If I put a number between 0 and L, now that's positive. This one's also positive. If everything's positive, positive slope means increasing. So that's enough to tell me what happens with 0. Is it stable or unstable? It's unstable, because if I move off of it just a little bit, I'm brought away. Okay, so this P equals L, this guy's unstable. Oh, sorry, 0 is unstable. Okay, so what about L? Well, we already know what happens on one side, but that's not enough for us to know exactly. So what happens if I'm bigger than L? This is positive, and now this one's going to be negative. Well, positive times negative is negative, which means I'm decreasing, and that makes that guy stable. Okay, so just looking at that, we now have these two equilibria, one's stable, one's unstable. So what this population wants to do, if we're going to use this model, it wants to go to L. It wants to reach that carrying capacity. So this model, we call this logistic growth. And I'm pretty sure I solved this last time that we looked at this. I seem to recall. If not, I mean, how are you going to solve this? What type of differential equation? Let's classify it again. Order? First. It's first order. Linear? Nope, because when we multiply that p through, we get a p squared. So we can't use those methods. Is it separable?
I think so.
It absolutely is. All autonomous differential equations are separable. So we can separate it. It leads to partial fractions. And I really feel like I kind of walked you through real quick the nuts and bolts of it. Okay. But logistic growth does lead to an equation that we can solve for that has exponentials in it, but it's not exponential. In fact, the exponential piece is in the denominator of the fraction once everything is said and done. All right, but we can solve it. All right, and we solve it by separating. I'm not going to torture you with the algebra at this point. I know you don't really care. All right. Plus, we can just put it into a computer and have it do it for us anyway. All right, so that's what happens when we throw in a carrying capacity. And while that's great, it makes it more realistic. If we want to do a better job of population modeling, we really want to introduce something else. So another thing we can introduce is what's called a threshold. And what a threshold is, this is a minimum P for the population to continue. Meaning, if we drop below the threshold, we die out. Now, if you think about this in terms of the real world, this is realistic. Eventually, we have too few of a species and they go extinct. Right? There have been animals that have gone extinct in your lifetime even. They're not usually big and flashy, but it happens. Right? Okay, so threshold is another way we can kind of add to this model to make it better. All right, well, what's that going to make our P prime look like? Well, we want to start the same way. We want it to grow exponentially. And if you're going to put a threshold, you might as well have a carrying capacity, because it'd be kind of silly to just say, well, if you're above the threshold, you grow forever. Nah, that's not true. So let's keep our carrying capacity. But now we're going to want something in here with our threshold. And I'm going to call threshold T. Now, I wrote this, but we're going to investigate if this does what we want it to do. If not, we'll adjust it. But having something like a T minus P definitely makes sense. It works just like the L minus P. And in fact, now, in terms of equilibria, what are our different equilibrium values? So still 0 and L, but now also T. And that should kind of make sense, right? That if we're right at our threshold, we should be able to maintain that. But obviously, if we dip below that threshold, we need to die off. If we get above that threshold, we should grow until we reach our carrying capacity.
So at there, it can stay stable.
I mean, that's what this is suggesting. And I mean, that's kind of the idea of a threshold, right? Like if you're at that number, you're creating, new critters as fast as they're dying out. So you're staying right there. And technically, you're probably still going to die out because nothing is perfect mathematically, right? This is math world versus real world anyway, right? But the idea is that, that'd be fine as an equilibrium, right? But it should be such that if we get bigger than that, we're able to grow. And if we get less than that, we die out. Okay, so now if we kind of look at this phase diagram, we're going to have 0, T, and L. Now, what I'm going to draw here are what we need to have happen for this model to work. If we are bigger than L, what needs to happen? Our population has to go down. So we're going to need it to do this. If it's under L, the assumption is we should be able to grow to it. Right? So if we're above the threshold but below L, we should grow. What if we are below the threshold? We need to die off as we go to 0. And then below 0, I don't really care about that because I'm not going to talk about negative numbers of blue whales or whatever we're talking about. Right? So I'm not going to worry about that. Okay, so my question is, does that differential equation do that? So let's think about something slightly bigger than 0. Okay, so we're less than T, but bigger than 0. So that means our population P is positive. What about L minus P? Positive. We're below threshold, we're below carrying capacity. So positive, positive. And what about this last one? If I'm less than T, that's also positive. So this differential equation, if I put in a number that's in here, leads to a positive derivative, which means I'm increasing.
No good.
Okay, that's no good.
Switch T and P.
What I need is for it to be decreasing. So how about I just put a minus sign on there? I'll get back to your maybe P minus T in a second, but let's just put this on there now. Now we're definitely good in here. Because this was plus, plus, plus with a minus, negative is decreasing. Let's make sure it works for the others though. What if I'm between T and L? So bigger than T, but less than L. Positive, positive. If I'm bigger than T, that's going to be negative. So I've got a negative, positive, positive, negative. 2 negatives make a plus. We're increasing. Okay, so far so good. Let's go to what if we're bigger than L? Positive, negative, negative. So I've got negative, positive, negative, negative. 3 negatives is a negative. It's doing what I want. Okay, so our first instinct is just putting in that T minus P did the wrong thing. But we were able to account for it by just throwing in a minus sign. Now, what you'll usually see though is instead of having that negative out front, we just distributed in the last one and then switch the signs. So this is equivalent and still is kind of showing you that relationship between P and T. All right, so there's our differential equation. The K is still the same K growth rate, but L is your carrying capacity and T is your threshold. All right, so can we solve this one?
Yes, we can.
Absolutely can. It is separable. It's going to lead to partial fractions with 3 fractions this time, but no big deal. right? And it will lead to something that does have exponents in it, because it's still based on exponential growth. It's just way more complicated than c to the kt. All right, well, there you go. We've now built our differential equation that models that situation. So check it out. Every step we took down here, we made it more realistic, but at the end of the day, it became more complicated. And just to let you guys know, because I know you're all going into science, that's the balance you got to find. Is how can we still make it close enough to the real world, but the math's still doable? Because if you include everything that you can possibly imagine, sometimes that math is so gnarly that like it's just not doable. Or you can use a computer to get you an approximation, but then that approximation fails you later. Weather is a great example. Right? When they forecast weather, they have all kinds of models that they run to try to predict the weather. But we all know how well they predict the weather. Not well. Right? I mean, decent. But it's, how often are we told, oh, we're going to get 3 feet of snow, and we get none? Or it's going to be a beautiful day today, and a storm hits us, right? Or what, like, because it's very, very complicated, and all the assumptions they make that help their model run are such that that model's prediction is only good for a short amount of time. And I don't know how you guys are personally with weather. Like when there's a 10-day forecast, I don't even pay attention to the end of that. Tomorrow, yeah, I'll look at tomorrow's forecast and be fairly confident. 2 days, I start questioning it a lot, right? Just because I know how fast models can diverge from the real world. Anyway, point is, you got to make that balance. This is not so bad that we can't do the math. We could, like, I could give this to you as a homework problem, and you could do it. You would bitch and moan about all the algebra you have to do and all that kind of stuff, but you have the tools to do it. But even this is simplified. Because, like, what does this not take into account? Or what are assumptions of this model that maybe aren't really valid?
One example is modeling, like, what kind of population?
Sorry, say again. What
What kind of population?
it could be anything, probably like an animal of some type.
Well, we can only have whole numbers.
Okay, so there's one big thing, is that when we talk about populations of critters, they are not continuous functions. We have a whole number of bear. There's no such thing as 13.384 bears. I mean, I guess kind of if we've got a decomposing body somewhere, but then we count that as a 0. Okay, so there is a big limitation already, is that this is saying this is a continuous population, but it's not. All right, what else? How about I'll give you one. Think about that carrying capacity. This is suggesting that that carrying capacity is always the same. Is that necessarily going to be true? Like, let's talk about a rabbit population that's out in the middle of some prairie somewhere. Are the amount of resources available going to be like static? No. What happens if we have a drought and now there aren't as many plants and can't have as many rabbits? Right? Or go the other way. Maybe there's like a banner year and there's tons of food. And, right? This doesn't account for seasonal variations that can impact your carrying capacity or your threshold. How about K? What is K again?
Growth rate.
It's a growth rate. Is that always going to be the same? No. You want a good example, look at like human populations. Specifically, look at like in the United States. What's happened to the growth rate in the United States? It's declined, and in fact, we're to the point now where our population is decreasing if it weren't for immigration. If you look just at childbirth, more people are dying than are being born. So the U.S. population is dying off. Has it always been that way?
No.
Absolutely not. Baby boomers, your parents, well, your grandparents probably, are great examples. Like that generation, there was a huge, huge growth rate in the U.S. population at that point in time. Right? So this is assuming K is constant. That's not necessarily a good assumption, especially for long term. You want to use this model for a couple of years, you're probably all right. You want to use this model for a century, going to fail you. Right, what else does this take into account? How about this? Rabbits. What else determines the population of rabbits other than rabbits?
Wolves.
The things that eat rabbits. Right? So what if we've got a predator-prey situation? I can't adequately model rabbit population if I don't know coyote population. And coyote population is probably going to be dependent on rabbit population. Well, we want to throw that in, we can. We don't have nearly the tools to do that yet, but we will by the end of this term. Because that leads to a system of differential equations. You've got an R prime and a C prime. Rabbit population and coyote population changes. And that rabbit population's change depends on how many rabbits are there, but also how many coyotes are there. And the coyotes, vice versa, leads to a system of equations that's going to bring back matrices and eigenvalues and eigenvectors and all that great stuff. Dude, it's a system. What do you expect? Right? So, like, we can keep building on these really basic, like, this is a really basic idea. Really simple differential equation. Like, I dare say trivial. Super easy to solve. We don't even have to think about it. And yet, if we take that and run with it, we can make it as complicated as we want. But each step of that is making it more realistic than before. All right, I think it's a good place to stop. I think we're probably out of time anyway. Oh yeah, we're out of time. So what we'll do next time on Friday is more applications. I'll show you things that have nothing to do with population growth. And yet I'm still going to tie it back to population growth.